Okay, let's move along and evaluate the electric field of a dipole. Okay, just so you guys remember, right, our electric field is equal to the negative gradient of the potential. Okay, we're going to use spherical coordinates because that just makes more sense. We could, of course, use Cartesian coordinates, but in terms of visualizing it, it makes more sense to use spherical coordinates. And also, we know that v, the way that we've calculated it, is in terms of r, which is a radial distance. That's part of the spherical coordinate system. All right, so I need to take the gradient in spherical coordinates. I can look in the back of the book and figure out how I need to do that. Each component of my grad vector is given in spherical coordinates by what I'm writing out here. And figuring out what these are in spherical coordinates, by the way, is more like a geometry thing. It's just making it so that when you take the gradient with respect to an angular displacement, it still has the same units and the same meaning as taking the gradient with respect to a position. Okay, so let's figure out what we need to do to take the gradient here of our potential in spherical coordinates. Okay, when I solved the problem before, I made it nice and I had the dipole aligned with the z direction. So I'm going to go ahead and do that again. So this will be my z direction. And I'm going to make it, and again, I can pick whatever coordinate system I want, just like any other problem. So this just makes my life easier. That's my dipole moment. Okay. I'll use a different color. Here's my point P up here where I'm trying to evaluate the potential. So here's my R vector. Okay. And here, in this case, they're separated by some angle theta. And notice this angle theta, which is measured from our positive z-axis, is the same as the theta that we use when we're defining spherical coordinates. Okay, so this particular configuration of P along the z-axis, this is nice because then I can write, okay, so now when I do P dotted with the r hat vector, okay, I get the magnitude of P just like normally I would. The magnitude of R is just 1 because that's a unit vector times the cosine of the angle between them. It would always be times the cosine of the angle between them, but this one's particularly useful because if I align it the way that I did, this is the same theta in our spherical coordinate system. Okay, so that makes it handy. All right, so if I do that, then I can write the potential now as 1 over 4 pi epsilon naught P over cosine theta divided by r squared. Okay, you can note about this, there is no phi dependence. Okay, so it's symmetric to any rotation about our z-axis. Okay, so if I imagine rotating this kind of around the z-axis, right, our potential aura field is not going to change. Okay, so now the last thing I need to do is just calculate this guy here. And this is going to be equal to, right, our magnitude of the electric field in the r direction times r hat plus the magnitude of the electric field in the theta direction times theta hat. That's a pretty easy, these guys are pretty easy to apply. I just need to take the gradient of our potential with respect to r to get this component, and then the gradient of the potential with respect to theta to get this component. That's straightforward. So the P comes out, then you get 4 pi epsilon naught, okay, and you're left with 2 cosine theta in the r hat direction plus sine of theta in the theta hat direction. Sweet. Okay, that's our electric field of a dipole consisting of two opposite charges, as long as we are, again, far away. So that's actually worth noting, because that's kind of the whole point of this multipole expansion. Okay, so this is for R much, much greater than D. Okay, so this is a special case. If I were really, really close to those two charges, the electric field would actually diverge from this. Okay, so drawing this electric field can be kind of fun and a little bit challenging. So let's go ahead and attempt to do that. To do that, I'm just going to quickly draw a coordinate system here. Okay, and on that coordinate system, I'm going to draw a circle, and there's a reason why I'm going to do that. I'll describe it in a second. Okay, so if I want to try to figure out how to draw this, it can be a little bit challenging because I think we're really used to x hat, y hat, or z hat, okay, instead of the unit vectors r hat and theta hat, okay. But just like any vector can be written as a sum of perpendicular Cartesian vectors, so that would be x hat, y hat, x hat, y hat, z hat, okay, you can write a vector as a sum of perpendicular r hat, theta hat, phi hat. Okay, so what do those vectors look like? Well, if I come over to the circle, I drew it because it would help me. If I define some points here along the circle, I can actually draw what those vectors look like at those points. Okay, so at each of these points, the r hat vector is going to point perpendicular to the circle, and it's basically pointing in a direction. If I were to draw a point from the origin to that point, it would point in the same direction as the r hat vector. Okay, so wherever I draw a point in space, the r hat vector is going to point radially away from the origin. If you wanted to calculate what the r hat vector, the components would be from an x, y, and z vector at any particular place, you would do it according to this formula in the back of the book. In this case, we're not going to have any phi dependence. So we could just say that phi is 0 or something like that. Okay, if we say that this is the x-axis, then we're actually in a plane where phi is equal to 0. Phi, the angle, would be measured kind of from this plane out towards me or out of the paper. Okay, so that works out. If phi is equal to 0, then for this particular configuration, we would be getting r being equal to the sine of theta x hat plus cosine of theta z hat. Okay, so hopefully that makes sense here. It would be when theta is equal to pi over 2, r hat would be pointing in the positive x direction. When theta is equal to pi, then r hat would be pointed in the negative z hat direction, and then we can go around like that. Okay, if I look in the back of the book, I can also find a equation for the unit vector formula for theta hat. This is with phi equal to 0. Okay, theta hat would be cosine of theta times the cosine of phi x hat plus cosine of theta sine of phi y hat minus the sine of theta z hat. Again, I can apply for this particular plane that we're looking at, phi being equal to 0. When I do that, then I end up with cosine of theta x hat minus the sine of theta z hat. Okay, again, if I were to go around here and pick my spots, here I'm at theta is equal to 0. When I do that, I'm going to get a vector that points perpendicular to the r hat vector in this case, the positive x direction. This would be my theta hat vector. Okay, when I'm down here, I'm going to get a vector that points in the negative z hat direction. Okay, when I come all the way down here, I'm going to get a vector that points in the negative x direction, still perpendicular to r hat. Okay, and I can go ahead and follow this around. It gets a little bit complicated because we're still going to be measuring that theta vector, okay, from this z-axis. So actually, when I go over to this other side, I can go ahead and draw these guys into. We're still getting vectors that are pointing perpendicular to r hat, but down. Okay, so why bother with all of that? Well, we're trying to sketch an electric field that in spherical coordinates looks like what we just found. So 2 cosine theta r hat plus sine of theta hat. Okay, so understanding how these unit vectors work is going to help us sketch this field. Okay, so for example, I know that at theta equals 2 pi, or pi over 2, it's all in our theta hat direction. And I know that when theta is equal to 0 or pi, it's all in the r hat direction. Okay, so if I were to draw another little coordinate system here, and when I think about a point up here, theta is going to be equal to 0. So my field's going to be from that point, all in the r direction. So I'm going to draw a little field vector there. Down here, theta is equal to pi. So actually, I'm going to get a negative sign here, and it's going to be in the negative r direction. So the positive r direction would point down. The negative r direction is going to point up right here. Okay, if I go over to this point over here, theta is equal to 2 pi. So I know that my field is going to point down there. Okay, similarly over here, it's going to point down, and these would actually be a little bit shorter, about half the length of these. If I were to draw them with the correct magnitudes, that would look something like that. That would look something like that. And I can continue. Draw another loop. Sketch another loop. Okay, but the main point is when you're close to this axis, it's pointing in the radial direction. Let me draw some arrows here, radially up on the top and also up on the bottom here. And then when you're at the axis, it's pointed perpendicular here to our x-axis. Downward, it's symmetric for rotation about this axis. And if I really wanted to find just what the field is at a particular point up here, I could calculate the magnitudes of these two components, and I could draw them out. Okay, this one obviously would have a longer component that would be tangent to that circle rather than perpendicular to the circle, but it would still work in the same way.